Hey everyone, today we will be doing our first example for automatic speech recognition, specifically implementing the DeepSpeech2 architecture. So there are two prerequisites going into this video. The first one is that you're already comfortable or understand the CTC loss, the connectionist temporal classification loss. I already have an entire video describing exactly how that algorithm works, so I will link that down below and put a card above. And also you are comfortable or have heard of spectrograms, right? Converting signals to spectrograms. So the spectrogram is what we are going to be using to convert our audio to essentially something that looks like a picture of an audio that describes the time frequency information of our raw audio, and our neural network will be trained on these spectrograms. So go ahead and take a look at my video there on MelSpectrograms just to get a general idea of what's going on. So let's do a really quick recap of what we're trying to solve in automatic speech recognition, though we talk about this in the CTC loss video. Speech is typically recorded as like a waveform. So you'll kind of have like a waveform of stuff being said. And then what we have is a transcript that goes with this waveform. So let's say our transcript is hello world, right? That's the statement that's being said. Now the problem is, unlike a language problem, we don't have a one-to-one mapping because I don't know what parts of this audio makes the H sound, what parts of the audio makes the E sound, what parts of the audio makes the L sound. So for example, obviously this waveform is fake, but let's just say this part here is the H sound. And then the E is kind of a short sound. So let's say we have like an E sound here, and we have some like the L sound here, the L sound here. We'll have like an O sound here, and then we'll have like, a space in between. So we'll have like a space, let's just say, and then you'll have like the world, maybe the O is short here, R, ... right? So whatever. The entire point of the CTC loss is to learn the alignment of this many-to-one mapping, because this H here corresponds to many different numbers from our waveform, right? In a range of numbers. So it kind of goes with this entire time range here. And then the E goes with this entire time range here, and the L goes with this entire time range here, ... We just don't know what these time ranges are ourselves, right? We don't really know what they are ahead of time. So we need to train a model that aligns our transcript to the audio. And that's exactly what the CTC loss does. So go ahead and take a look at that video if you're a little bit confused. Now, typically we don't actually train or align our transcript directly to the audio. Instead, we align them to some type of a feature extraction. And so the first step of deep speech will be to extract some convolution features. So we'll kind of pass all of this through some convolutions, right? Convolutions. And we're going to extract some features, right? So these are our sequence. Typically, it'll be some type of downsampling, right? We're going to downsample our signal, ... And then these features represent, different times of this audio itself. And of course, we won't be working on the raw waveforms. We'll be working on the spectrogram, but that's fine. We'll look at wave-to-vec in the future where we'll be working on raw waveforms. And then what we're going to have is, of course, the convolutions just extracted features of different time steps of the audio or spectrogram. We need to now learn the sequence relationship, right? How the different time steps are related to each other. So to do sequence modeling, there's all sorts of architectures out there. We can use an LSTM, GRU, just a standard RNN, whatever you want. So we have kind of these architectures, and that's also going to, of course, output some, things that will represent the interrelationship between the different time steps. Of course, you could also use a transformer here, right? Transformer. And we'll be doing that in a future video. And so we end up with this architecture that looks kind of like this. And of course, we still have our transcript hello world. And so the question is, which parts of these embeddings, let's say the first two go with the H, and then the next one goes with the E, and then like the next ones go with the first L, and the next ones go with the second L, ... And so this is an important part of the entire speech recognition problem of aligning our transcript to our embeddings. And this is performed through the CTC loss, right? It is the alignment loss. So this is all well and good, but we do have one little bit of problem. So when we do the alignment, so if it's a many-to-one mapping, then what our model will end up predicting, let's say the word was eat, right? EAT. let's say that's a word, and our model had kind of these outputs. Let's say there's 6 of them. So you have these things here. So we could say that maybe our final output will be E, A, T, T. Let's just say. So the E is the first embedding, and then it lines A to kind of these 3 here, and then T to these last 2. So after that, all we need to do is take all of this and collapse it down, right? Repeating letters should get collapsed down, so it should be E, A, T, right? The E goes here, all the A's become an A, and then all the T's become a T. So that's how we'll actually do inferencing in the future. Now, the problem here is, what about a word like hello? If we have a word like hello, Hello, and let's just stick a couple more embeddings here because it's a little bit longer. So we'll have an H. Let's say we have a couple H's. We'll have some E's. We'll have some of the L sounds and then an O sound. Well, this, when collapsed, will become HE, and all of the L's will just become an L and then an O. This will not work, right? Because we need 2 L's in sequence, but with the collapsing method that we have right now, that's not actually possible. So this is why in our CTC loss, we introduce a special blank token. So for us to have, for the neural network to essentially predict repeating letters, it needs to put a blank token in between them. So now these 2 H's will become an H, these become an E, these become an L. The blank we'll just ignore. This one L is just an L, and this O is an O. So now we have hello. So our vocabulary, the tokenizer essentially, is going to be just a bunch of characters, a space, right, to have space between words, and we'll have this kind of blank character, blank token here. And this blank token is especially important for our CTC. So that's essentially a super quick recap of that previous CTC video. So go ahead and take a look and see the inner workings of the forward algorithm, right? It's a dynamic programming algorithm to actually pull off the CTC loss. But for now, that should be enough to just give a quick recap of everything we've talked about. So that's exactly what DeepSpeech is. DeepSpeech2 is trained on raw spectrograms or MelSpectrograms, which are better for actual speech applications. We're going to then go ahead and train some convolutions on them. We're then going to train some recurrent neural networks on them. And then we have a fully connected layer at the end to go ahead and do our prediction of what token is this time step. And so I'm just going to go ahead and copy paste these imports here just so we have everything. Pretty standard imports. We just have some extra stuff with Torch Audio that we briefly looked at before. And we're using a package called GWR to compute our word error rate, which is a typical metric used for speech recognition, right? So what's your word error rate? And the other thing we're going to do is, of course, we could actually write this tokenizer pretty easily, right? So just have like all the characters A through Z, and then have a space and then a blank and any other special tokens you could think of. We could have all of this stuff if we wanted, and then write something that did the collapsing and all that. That would be fine, but we're just going to go ahead and use a pre-built tokenizer as well. So to keep things simple, we're just going to go ahead and use the Hugging Face tokenizer, the Wave to Vec2 tokenizer. So tokenizer will be the, let's make it a little bit bigger. Tokenizer is going to be the Wave to Vec2 tokenizer dot from pre-trained, and we'll use the Facebook Wave to Vec2 base tokenizer. Of course, we could have written our own tokenizer that essentially did, and it looks like I misspelled something, Wave to Vec2 CTC tokenizer. There we go. We could have written our own, but might as well just use one that exists just to keep things simple. This tokenizer is very simple. As you will see, it has essentially the characters A through Z. It has a separator token. It has some pad tokens and whatever. And just for our simplicity, we're going to ignore all of this stuff here. We don't need any of that for today. We'll need some of this for our Wave to Vec implementation in the future. We're just going to use our A through Z, our space token, right? So space between letters, and we're going to be using our pad token as our blank token, right? For repeating characters and that sort of stuff. So that's what we're going to be doing. So let's go ahead and get started by first implementing our data set and computing spectrogram. So this should help us ground exactly what we're trying to do. So to write our data set, it should be pretty simple. I have already gone ahead and downloaded the LibreSpeech data. You can download LibreSpeech right here in OpenSLR. So OpenSLR. Here we go. So you can download this data set right here. They have a dev clean, dev other, test clean, test other, train clean, train other, you can see there's 960 hours worth of training data here with parallel transcripts, right? So we have both audio and transcripts. You can go ahead and download this, and I've already downloaded it right here. So if we look at LibreSpeech, it's right here. So this is the data we'll be working with. The data set is pretty straightforward. What we have is for every single split, let's look at like dev other, for example, 116, we have all these subfolders. We have a bunch of FLACs. These are the actual audios themselves. And then we have, for each of the FLACs, we have their corresponding transcripts. So that's everything we need to set this up. So we have audio, we have transcripts. So we'll be writing a data loader that kind of loads all of this stuff. And of course, if you're wondering what's the difference between dev other, or like what's the difference clean and other, clean is just cleaner, higher quality data. Other may not be as clean. It may not be essentially as validated as the clean data, but it's good because we just have a lot of data and all of it is pretty good for the most part. And LibreSpeech is one of the most popular data sets to train ASR models on, so that's what we'll be using. So let's go ahead and write this data set. Class LibreSpeech data set. It's going to be a standard PyTorch data set. Oh, I have Butterfingers. Let's fix that. All right, good. So we're going to do def init. We need our path to data root. That's just going to be path to that folder. And then include splits, right? So what is the splits we want? In our case, we're going to have train clean 100. We'll have train clean 360 for the 360-hour split, and then the train other 500. And of course, we also had the other two, but for now, let's just say we're loading the training split. So the training split will be on the training data. The validation will be on the other two, the dev clean and the test clean. So that's fine. We'll have our sampling rate. All of the LibreSpeech audio is already sampled to 16,000 samples per second, so we're kind of good to go. But just in case it's not, we're going to downsample to that or upsample, whatever it may be. And then num audio channels. This is all single channel audio, so it'll just be one channel. And so we're going to do self.sampling rate is going to be sampling rate. Self.num audio channels is num audio channels. And just as housekeeping, I expect my include splits to be a list. So if it's not, so if is instance include split. If it's a string, then go ahead and do include splits is equal to include splits. It's going to be just a list with include splits, just like that. Nice. Let's just make sure it's always a list. So now we're going to do, of course, we have our self.LibreSpeech data. We're going to create a list of tuples, and each tuple is going to contain essentially the path to the audio file and its corresponding transcript. So we're going to do for split in include splits, include splits. So for every single one of these splits, and the easiest way to check this is going to be data is our LibreSpeech data set. Just like that. All right, what am I missing? Path to data root. That's going to be in mount data drive data, and then I think it's all lowercase, LibreSpeech. Good. Yeah, well, here, let's just check that real quick, that it's actually all lowercase os.list directory. Okay, it looks like that's not it. So it's LibreSpeech. There we go. So it's uppercase LibreSpeech. So let's fix that. All right. So there's our data. There's our splits. So that's what we're going to be using. So for every single one of these splits, we're going to first do path to split is going to be os.path.join. And we're going to join our path to the split, or path to data root, to our path to split, or just split in this case. That's our path to split. And then inside each of these folders, as you remember, there was essentially a bunch of subfolders. So the first subfolder is the speaker, and then the second subfolder is the section. So we're going to do for speaker in os.listdir path to split we can print out speaker. And let's just throw a break right here. You'll see we have a bunch of these speakers, right? So each speaker has a different identifier. So there's all their identifiers. So for every single speaker, we're going to then do our path to speaker. It's going to be os.path.join path to split and speaker. So there we go. And then, and I'm gonna throw a break here just so we don't loop through every single split. And I'm gonna put a break right here so we don't loop through every single speaker, so we can see one at a time. And lastly, we're gonna do for section in os.lister path to sections. There's smarter ways of doing this, but it's fine. We're just gonna do it this way. os.lister path to speaker. And then our print section. You'll see these are the sections inside each speaker. So each speaker has multiple sections that they may be speaking. So there you go. We can do path to section is going to be os.path.join path to speaker, and then the section that they're currently on. So that's the full path to there. And lastly, what are all the files inside each section? So we can do print os.lister, one more time, path to section. And this will give us the list of all of those FLAC files that we see here. There's this extra file here called audio duration. This will not be inside your download of LibreSpeech. Ignore this. We'll be generating this later for the WaveShift stuff because of memory issues. For now, we don't have to worry about it, so just ignore audio duration. Other than that, though, we can go ahead. We now have all the files, so these will be the files. There's there. And our transcript file is going to be path for path in files if.text in path. And we'll just grab the first thing because there's only one thing that has this transcript file. So this is going to be path for path in files. There we go. So this is our transcript.text, just like we saw before. So now that we have everything, let's go ahead and load those transcripts. We're going to do with open, and we're going to do os.path.join, and we're going to join the paths to the section, path to section, to our transcript file. Just like that, we're going to open it in reading mode as f, and transcripts is equal to f.readlines print transcripts. And there we go. We now have all of our transcripts, and we have their corresponding ID. So for this audio, this is its transcript. For this audio, this is its transcript, ... And we'll have to split all that up. So let's go ahead and do the last cleanup. For a line in transcripts, right? So for every single sample, essentially, of pairs, we're going to do split line is equal to line.split. We'll just split it by white space. This is going to be split. Line, and we can do print split line, and let's just throw another break in there. And so we just went and split everything up. We have this one as our actual ID, and then all of this stuff was the actual sentence that went with that ID. So we just need to put it all back together. Our audio root is going to be split line. It's just the first thing, and then the audio file will just be the audio root plus .FLAC, right? It's just a FLAC file, so standard audio file or audio format file. It could have also been a WAV, but in this case, LibreSpeech is just stored as FLAC files, so there we go. And then on the other one, the full path to audio file is going to be os.path.join, and we're going to do the full path. It's going to be the path to section, and then it's going to be the audio file. So this gives me the full path to that specific audio file. And then our transcript is going to be, we're going to go ahead and put it back together, .join, split line, and it's going to be everything else, right? So 1 to the end. So ignoring this first thing. So it's going to be from 1 to end, just like that. And then just in case there's any extra random white spaces or something, we'll just go ahead and clean that up with the strip. So print transcript. Strip will get rid of this, any new line characters or anything. So this is our corresponding transcript. Now, in our implementation, like wave to vec, we will only be training on uppercase letters. So there won't be, case sensitive or anything like that. We're just going to do uppercase to keep it simple. More advanced ASR models like Whisper and stuff will be like it'll have uppercase and lowercase and multiple languages and be much more complicated. So we're just going to stick to this one. So that is finally our transcript. And so now we can store in self.LibreSpeechData.append. And like I promised, we're going to have a tuple of our path or full path to audio file. So that's our full path to audio file. And then we will store in here our corresponding transcript. And so that will go ahead and create our data set. So if we look at the full data set, this takes just a second to run, but let's look here. Print len self.LibreSpeechData. This will take a second, but we can see we have about 281,000 samples of audio text pairs. And this adds up to about 960 hours worth of audio. So that's a good start. Now we need two things. So as promised, our audio will be trained on spectrograms. So that's what we need to do. We need to convert it to a spectrogram. So to do that, we could, of course, use Librosa or another con package, but we'll be using Torch Audio just to keep things simple. So self.audio to mels. It's going to be t.MelSpectrogram. And to the MelSpectrogram, so this is a standard transform. So we can take our audio, convert it to a MelSpectrogram. All we need to do is provide it. What is the sampling rate of the audio? Sampling rate is sampling rate. And nmels is 80. So everything else about the MelSpectrogram, we will keep default. So just to make sure we look at what the defaults are. In Torch Audio, our MelSpectrogram looks like this. It assumes a sampling rate of 16,000. That's what we have. We'll be using 400 FFT bins, essentially, NFFT, with a window length set to default of NFFT. So our window length will also be 400, and our hop length, by default, will be half the window length. So essentially, our window size, the Hamming window, I believe it uses by default, or the Han window. So the Han window it uses by default will be of length 400, and then we'll be moving over by 200 every time. So we have a 200 sample overlap between the different windows. Again, if you're a little bit confused about this stuff, just go ahead and look online of how spectrograms and how short time Fourier transforms work. But we're just going to keep going because we'll be using their defaults right here. So that's our audio to Mel. And as we're going to see in just a second when we implement it, the Mel values at the end actually aren't that helpful. We typically train on the log transform or just to convert to decibels, right? So decibels a log transform. So we're going to go ahead and do that. Self.amplitude to decibel is going to be transform.amplitude to dB. And we're just going to say top dB is 80.0, right? Just set a maximum threshold so it doesn't exceed that. Looks like we have a small mistake here. Init got a sampling rate, or it should not be sampling rate, it should be sample rate, and we are now good. All right, so def len self, and we'll just return len self.LibreSpeechData, right? That's how many samples are in this data set. And now we can define our get item. And this will be pretty straightforward for index. So for a specific index, we're going to get a path to audio and a transcript, right? Its corresponding transcript is self.LibreSpeechData index. Just go ahead and grab that tuple. Now that we have that, we need to load our audio. We're just going to go ahead and use Torch. So we're going to do audio. And then the original sampling rate is going to be torch audio.load path to audio. And we're going to go ahead and just pre-normalize it here. So normalize is true. And just so we're clear about it, because we're just using all this stuff, so torch audio load, just so we can see some of the defaults here as well when it comes to audio stuff, because it's a little bit different from what you may have seen before. Normalize by default is set to true, and it does this, right? So when true, it converts it to a native sampling type of float 32. So instead of being from like 0 to 255 or whatever the bit depth was of the original audio, it's probably higher for our FLAC files. Whatever it may be, it's going to scale everything between -1 and 1, being in float 32 precision. So that's why we're going to be using this, just to keep it simple. So we have that. That's going to go ahead and load an audio. Let's go ahead and take a look at that. So we're going to do for sample in data. We're going to break, and we're going to print audio here. Let's see what that looks like. And also, just to keep our loading time short, we're going to include splits, and we're just going to look at the, let's just look at one of them instead of all of them. So we'll just do include splits is, include splits is just that, just to keep it quick. All right, so there is our tensor that we've loaded. If we look at the min value, it's, something like that. If we look at the max value, it looks like something like that. If we set our normalized to false, then you'll see it'll be in the original int16 in this case, right? So integer value. So in the same way that images are values between 0 and 255, audio and its 16-bit, right, will have its own range. But we don't typically want that. We want it to just be between -1 and 1. So we are now good to go. So it should be true. So we have our audio. Now, just a quick sanity check. If the original sampling rate does not equal to self.sampling rate, so if it's not, then we need to resample our audio. And audio is torch audio.functional.resample. I'm going to resample this audio. The original frequency is the original sampling rate, and the new frequency is going to be self.sampling rates. Go ahead and resample the audio. Do keep in mind though, so we talked about aliasing in that introduction to audio processing stuff. Just make sure you're keeping an eye on kind of the frequency range of the audio we're working on and how your sampling rate affects that because of the Nyquist stuff. So either way, we should be good to go here because our audio is already 16,000, so this line won't even run anyway. So now let's go ahead and create our MelSpectrogram. So we're going to do mel is going to be self.audio to mels. And we're going to pass in our audio. So when we do this, when we print out our mel, for example, we'll get something like this, right? So here's our MelSpectrogram. We can look at the shape of it, which will be a little bit more helpful. It's 1 by 80 by 1127. So where did this come from? The 80 is coming because we have 80 bins, right? So 80 mel bins at the end. And we have 1127 here because after we did the sliding window of the Han window on our audio, we ended up with this much, right? So because we had a 400 window size with 200 overlap. So there we go. That's just what it ended up being at the end. We can also do print audio.shape. The original audio was of this size, right? So we've done actually quite a bit of compression here, right? We've gone down quite a bit because again, we did a 400 window size and then moved over by 200 every time. So we ended up with 1127 time steps with 80 mel bins at each of those steps. Now, if we actually look at this real quick, if we do, let's just throw, actually, I think we have it already. We do plt.inshow. If we look at the mel, and this probably won't work because there's too many indexes. Okay, and then we do plt. I guess you can already see, but let's throw a quick plt.fig size at the top, just so it's easy to see. You can see there's actually not a lot of information in here. It's all dark, and you have some of these hotspots at the top, and that's because the MelSpectrograms on their own are not the most helpful. We typically look at the log transform of these MelSpectrograms, or just convert to decibels, which is a log transform. So let's go ahead and just convert it to decibels. So mel is going to be self.amplitude to dB, the other transform we made, and mel. And now you can see we can see the spectral information much more clearly of what's going on. We can see there's kind of actual audio in these areas because we can see the different frequencies lighting up at the different time steps. We can see the different harmonics, and we can also see that there is no speech happening in these blank areas, right? So no one's speaking in those. So kind of cool. It's essentially a picture of the audio itself, and there's a lot more you can piece out from the spectrograms, but we're gonna leave it at that just to keep it simple. So that's our spectrogram. Now, of course, neural networks love if we print mel.min, mel.max. It's quite a range. Neural networks typically like to train on nicely normalized data. So we're just gonna go ahead and just quickly normalize this. We're gonna do mel is equal to mel minus mel.mean. We're gonna essentially do a standard normalization here. Subtract the mean, divide by the standard deviation. Mel dot standard deviation, and and we'll just add a 1e minus 6 here just so we don't have a divide by 0 error. And so that's our final Mel transform. Of course, we need our transcript as well. So our tokenized transcript is going to be just torch.tensor tokenizer.encode, because again, we're just using the default tokenizer from the Hugging Face wave to vec just to keep our life simple. But we could have easily just written a simple tokenizer with those couple of characters. So here's our tokenized text. And we have, as you can see, like I believe the 4s were our spaces between the tokens, right? So the spaces between the words. So we are now good to go. We have our tokenizer, our tokenized data, we have our MelSpectrogram. So we're going to go ahead and return it. We're going to do a sample. It's going to be equal to input values, and this will be our Mel. Our Mel transform has currently the dimension. So again, let's print out Mel.shape. Let's comment you out. We have this 1 by 80 by 1127. We don't really need this one, so we're going to go ahead and get rid of it. So we're going to do Mel 0. And the other thing is this ends up being essentially 80 features, right? We have 80 features and 1127 time steps. I like working in the batch by sequence length by feature dim. So we're going to do a transpose. So we have the time dimension first and then the feature dimension after, right? Just so it's a little bit closer to what I'm typically used to. But you can, of course, do it however you want. And our labels is going to be the tokenized transcript, just like that. Of course, something is slightly wrong. I just spelled tokenized transcript. There we go. All right, and now we can return our sample. So that's everything we need. And so just to make it clear, right, let's just paste all this in here. We're going to grab a sample, and this is the one we just looked at, right? So this is our MelSpectrogram. You can see it's transposed, right? So that's why I retransposed it again, just so it's a horizontal image rather than vertical, but either way, it's the same thing. So this is our MelSpectrogram. Of course, now that we are training our neural network, one thing we have to keep in mind is different audios are of different lengths. So of course, we need to pad the shorter audios to the longer ones. And so this is our collate function. So let's go ahead and write our collate function. And there's going to be a couple of caveats here that we need to keep in mind. The first one is what we want to do is use the packed padding method that recurrent neural networks work on. So you can imagine that if I have 16 audios in a batch, and let's say the first audio is 15 seconds long, but the second audio is only 2 seconds long. That means there's going to be essentially 13 seconds worth of pad tokens that we've added to the audio. And then when we process this with our recurrent neural network, actually training on the pad tokens is a waste of compute, right? There's no need to train on pad tokens because, first of all, the pad tokens shouldn't even be there to begin with. So in PyTorch, they support packed padded data. So what we do is remove all the pad tokens and then flatten it all. So it's just one sequence, and we just tell the LSTM which indexes or which time steps correspond to the different available tokens. This is going to make a little bit more sense when we do it, but the only requirement that we have is that our batch is sorted from longest to shortest. That's the only real prerequisite we have, but we can quickly do that. I'm going to write a collate function, pass in a batch, collate function, pass in our batch. And first it's going to be batch is going to be sorted. Actually, let's go ahead and print the batch out just so it's clear. And what we're going to have is loader is a data loader. It's going to wrap the data set from before. Let's do a batch size of 5. And our collate function is the collate function. And we're going to do batch is next iter loader. Let's just do that. All right. So we end up with all the samples from before. So we have the first sample, we have the input values, and we have the labels. And the second sample, we have the input values and then the labels. Third sample, input values, the labels. And each of these input values are that MelSpectrogram, right? The normalized MelSpectrogram. So what we need to do, so let's do batch, let's look at 0, and then we're going to look at the input values dot shape, right? So this was the 1127 time steps of that first sample, right? So that's this right here. It's 1127 long. And then the next one, let's look at the next one, is 1276 long. So this one's a little bit longer. The next one, this one's 1116 long. So it's a different, so each one of these are a different length. And what we want to do is just sort our data So we have the longest thing to the shortest thing. And the only reason we're doing this is because the padded data method that we're going to be passing to the recurrent neural network just expects it that way. And it'll make sense why when we actually look at it. So our new batch is going to be sorted. Very simple. We're going to sort the batch, and the key is going to be lambda x, and it's going to be x. We're going to look at the input values, and then we're going to look at the shape, 0. So we're going to sort it by the shape, and we want reverse equals true because we want it to go from greatest to least. So now when we print out batch, 0, and then we'll look at the input values dot shape, just like that. We're missing a invalid syntax. Lambda, we have key is equal to, not colon, equal to. There we go. So the first thing is 1276. The next thing is 1177. The next thing is 1127. So you can see now it's in descending order, right, of length. So that's the first step. We just go ahead and sort our batch like that. And now let's go ahead and grab everything. Our batch mels is going to be sample input values for sample in batch. And then similarly, we'll have their transcripts, right? So that's the batch mels. We'll have our batch transcripts. And then, of course, we'll have transcripts right here, or whatever I called it. So I called it labels. All right, labels. So we have our MelSpectrograms, we have our transcripts, but of course, each of these MelSpectrograms, right, for B in batch mels, print B.shape, each of these MelSpectrograms are in descending length, but they are of different lengths. So we need to pad the shorter things to the longer things. So let's go ahead and do that. But first, we're just gonna store some values that tell us the original sequence length of each audio before we did any of this padding stuff. So we're gonna do sequence length. It's gonna be torch.tensor. It's gonna be b.shape 0 for b in batch mels. Just go ahead and just store that for our own sanity and for the future, loss function and stuff that we're gonna be doing. So we're gonna need all of this stuff. And also we need a, let's just make sure this is in D type, is torch.long. We don't necessarily have to store the sequence length here. We could just figure it out from the padding and stuff in the future. Just, do a, if it's not pad, then it's not a part of it. But honestly, it's just more complicated to do it that way. Let's just store it right here. And so now that we have that, we're going to do our spectrograms. Our spectrograms. It's going to be torch, standard padding, torch.nn.utils.rnn.pad sequence, right? Go ahead and pad the sequence. It's going to be batch mels. It's going to be batch first equals true, and then padding value is 0. So we're going to essentially 0 pad all of the audios that are shorter, or the spectrograms that are shorter, to the longer ones. So very simply just 0 pad everything. And now if we look at our print spectrograms.shape, you'll notice a couple things. We have a batch size by sequence length by our kind of hidden size. But again, remember, if we were just doing transformers right off the bat, then this would probably be fine. This would be no problem. But we have a couple of convolutions at the beginning, right? The first thing in our deep speech architecture is convolutions. So let's go ahead and set this in the shape that a standard 2D convolution would expect. So this would be, let's go ahead and just add them in. So spectrograms is going to be spectrograms.unsqueeze 1, because PyTorch convolutions expects the shape of batch size by channels, by some height, by some width. And just to make our life a little bit simpler, again, you could leave it like this and it would be fine, but I would rather have it look like the picture here where it's long ways, just so our images kind of match what we're doing. You could also leave it this way, but it will just flip all of our convolutions, kind of the the shapes we provide, but that's fine. We're just gonna go ahead and do a dot transpose here again, and we're gonna do -1, -2. And so this is our final shape. We have batch size of 5, each image, quote unquote, but spectrogram has 1 channel. Each channel has a height of 80 and a width of 1276 in this case. But of course, many of the things here are pads, right? The 0 pads that we added in the end. So we have our spectrograms. Our target lengths right? We're going to need this as well. This is going to be for the loss specifically. The CTC loss needs to know what is the length of each of the targets. So it's going to be torch.tensor. And we're going to do len t for t in batch transcripts. And again, d type is torch.long. So there's, again, a couple of reasons we're doing this. The CTC loss is going to need this information. Our own implementation is going to actually need some of this information as well, just to make our life simpler. You'll see where this fits in a bit. So we're going to go ahead and just store some of this stuff. The sequence length is the sequence length of the original inputs, and our target length is the sequence length of our targets, right? The labels themselves. Now that we have all of that, we can do our packed transcript. It's going to be torch.cat batch transcripts. So in this case, if we print our packed transcripts, we just took all of our labels and just concatenated them into one thing. Well, how does that work? If everything's just one list, how do I know which tokens go with the first sample in the batch, which tokens go with the second sample in the batch? Well, I already know that because print target length tells me that the first 283 things in this list go with the first sample. The next 268 things go with the second sample. The next 201 things go with the third sample, ... The targets don't have to be sorted in this way because the targets are handled by the CTC loss, which doesn't really care about the order, but the inputs need to be sorted from longest to shortest because the recurrent neural networks that we'll be processing them with actually does care. So there we go. That is our total setup, and we can now return our batch. It's going to be equal to input values. It's going to be spectrograms. After that, we'll have our sequence lengths. This is going to be the sequence lengths that we just computed. We'll then have our labels. This will be our packed transcripts. And finally, we'll have our target lengths. That will be our target lengths. And we can return the batch, just like that. And so just to explain a little bit more of how these things look, let's go ahead and test it out. So first of all, when we run this, we'll see that our input data is of the shape 5 by 1 by 80 by 1276. So that's the data we're working with. But I know that of this 1276, the longest things first, so all 1276 things are valid. But in the next one, only the first 1177 are valid. All the other time steps are pad. And in the next sample, only the first 1127 samples are valid. All the samples after that are just pad ... We see our labels have this length. We just took all of the labels and concatenated them together. But I know the first 283 things in my labels is the first sample. The next 268 things in the label is the next sample, ... And you'll see how this all fits in just a bit. Of course, it'll be a little bit easier to visualize this if we also print this out. So I'll just paste this as well. They're just looping through our data and just visualizing each spectrogram. And you can see that here's the full spectrogram in the first one. In the second one, we have a spectrogram, but we added zero padding at the end. The third one, we had some more zero padding, more zero padding, more zero padding. So we have our spectrogram sorted from longest to shortest, and we just zero padded everything to the longest one. And we are now good to go. Now, here's a problem that I will ask. I want to train a convolutional neural network on this data. But the problem is that should the convolution also apply to the masked area or this padded area? Of course not, right? We don't, this pad should not be included anywhere in our training because this is just extra stuff we did to fill out the matrix. Unfortunately, with the convolution, there's no like nice method where we can just ignore it like we do in the RNN. So we have to think of another way of doing it. And this is, we essentially need to pre-compute what are the valid regions. So if we look at our convolution, for example, conv2d, PyTorch provides us a function that looks like this. PyTorch provides a function that tells us, given a specific kernel size, padding, dilation, and stride, if my input height is hin, then my output height will be this hout. And if my width is this size, then my output width will be this size. And this is always true, right? So this is their formulation of how they set up the convolution and kind of handle those edge cases. So this is the overall formula of what the output will be. This means that if I apply a convolution to my signal here, I know what the valid part of the signal is. right? So let's say I know that, let's say this whole signal here is of length 1276, but I know only the first 1177 things are valid. So when I do a convolution, I know if I had applied a convolution to something of length 1177, I know what that output size would be ahead of time because I have the formula for that size. So I want to make sure that I'll apply a convolution to the whole thing. I'll check what was the valid parts of the output based on the valid parts of the input, and then just remask that output back out. So this is a key step of how we're going to handle this. So let's go ahead and apply it. So this is essentially called a masked convolution. And so this is our formulation, right? So standard formula for our setup. So what I just shown before. So the idea is that, again, if I pass in a spectrogram with this length of 1276, but I only know I know that only the first 1002 time steps are valid. So let's go ahead and just adjust for that, right? We're going to apply the convolution to everything, compute what the output shape would have been if I just done the first 1002 things rather than all 1276 things, and then just mask out the difference, right? Mask out the part that's not valid. So let's go ahead and just kind of give it a try. So our convolution, oh, we don't need you. That's fine. So our convolution is going to be nn.conv2d, and our in channels is going to be 1, because if you remember, if we look at batch input values dot shape, right, we have 1 input channel. Okay, fine, we're going to have 1 input channel. The output channels are hyperparameters, completely up to you. For now, I'm just going to say out channels is also equal to 1, just to keep it simple. Okay, in channels, out channels. We then have a kernel size. Oh, let's keep that available right there. Now a question, what kernel size do you want to use? I will just go ahead and keep it simple, and we'll use a 3x3 kernel, just like that. Now they have a kernel, we need to have a stride. And so we're going to stride of, and here's another question you want to ask. Stride, I typically want to, the stride will essentially decompress our data, right? So if we use a stride of 2, everything will get halved. So my 80 features will get halved to 40, and my 1276 will get halved to whatever the half of 1276 is. And so that would be fine, but how we're going to do it is a stride of 1, 2. So we're going to only move in our 80 direction, we're going to move 1 over every time, essentially leaving our 80 alone. We're not going to change the number of features here. But our time dimension, we're going to move with a stride of 2, essentially downsampling this one by a factor of 2. So there we go. And to make sure that we don't change the size of this 80, we're just going to add some padding here. So we're going to do padding equals 1, 0. So we're going to pad in the horizontal direction by 1. So this will be, essentially we have our 80 features here. We're going to add a padding at the top, padding at the bottom, and then do our convolution that way. And so this is our final convolution. And if we look at the stride, is that padding equals 1, 0. So we're going to go ahead and print this out right here. And then we're going to print out, oh, it's being a little bit weird. Sorry about that. Don't know why. Let's just restart it. Okay, and then we're going to first print this out. And then we're going to print out the convolution output. So let's call this output is conv batch input values, right? The one that we're working with. And we're going to print output.shape. And you'll see that we essentially halved our dimension here, right? So we've not exactly half, but close to half. We could have done some padding to make sure it's an exact half, but this is fine. We've halved our temporal dimension. We've left our 80 mels as 80 mels, so we still have the same number of bins that we've done here, and all the other dimensions remain the same because we left the out channels the same, and batch size always stays the same. So we've gone ahead and done a downsample here in the temporal dimension, and the reason we're able to do that is because we had a stride of 2 in the horizontal direction, but a stride of 1 in the vertical direction, right? And we added a padding of 1. If we had made this a padding of 0, then you see we would have had a minor downsample in the mel dimension. We want to keep it as same as possible, so that's what we're going to do right here. So that is our setup, but like I mentioned, we did this convolution, but I know that some parts of this batch, right? Because in this sample, like the second sample, there was a bunch of pad tokens, right? We had these pads and these pads and these pads. So in my final output of 637, for each of these samples, the question I ask is, what part of this 637 time steps is valid, right? So which parts of this so essentially, we had this entire sequence here get compressed down to a sequence length of 637. But some of those steps in the 637 came from these pad tokens, and then some parts of the next sample came from these pad tokens, these pad tokens, these pad tokens. We want to make sure we zero out that effective area because we don't want to include stuff from padding into future gradients. So how's this going to work? Let's say padding, we did a padding of 0, our kernel size equals 3, and this is only in the horizontal direction. Right? We really only care about the stuff in the horizontal direction. We're keeping the vertical direction stuff the same. So we only care about the horizontal one. So we have a kernel size of 3, stride of 2, padding of 0. So kernel size 3, padding 0, and stride equals 2. So we're going to print our, just copy this in, so type it. Let's go ahead and print that. Right, so that's our input sequence length. So these were why we stored the sequence lengths ahead of time. Now I know in the first sample, my 1276 things were all true data. None of it was pad, which means all 637 outputs are valid in that first sample. But the question is in the next one, in the 1177, what's valid and what's not. So let's go ahead and apply our formula that we got from the PyTorch website, right? This is our formula. So let's go ahead and just do it. So the output shape, so output sequence length is going to be equal to torch.floor, right? So we can see there is a floor function around it, so torch.floor, and it's going to be our input. So it's going to be the input length. The input length is the sequence length, so batch sequence length, just like that, plus 2 times the padding, and let's just put a parenthesis around that so there's no confusion, minus kernel size -1 minus 1 divided by integer division by stride plus 1. And that's essentially the SIZE. That's the formula we had here, right? The input size plus 2 times padding minus, we have no dilation, so we don't care about that. So times the kernel size -1 minus 1 divided by the stride, integer division, and then plus 1. And that gives us our final output sequence length. So we can go ahead and print out the output sequence length. And so we can see of the 1276 things, the first, all 637 things are valid. So we're good to go. But if we had only 1177 here, only the first 588 outputs are valid. Everything from 588 to 637, all that extra stuff here, would have been pad. So we need to make sure we zero that out. Again, in the next sample of the 1127 things, it would have been downsampled down to 563. So that means everything between 563 and the 637 that it's padded to is invalid. We want to make sure we mask that out. And this is essentially the key idea that we want to make sure. We only want to keep the outputs of the parts of the convolution that came from valid signal, and we want to just mask out the stuff that's invalid. And the only way to do that is by masking the output. So how do we do that? We can do, our mask is going to be torch.nn.utils.rnn.pad sequence, and we're going to do a torch.ones I for I in output sequence length. We're going to do a padding value equals 0, and of course batch first equals true, just to keep it the same. So here's our mask. So we've created a mask of 1s and 0s, and the first one is of length 637, the next one's 588, next one's 563, 557, 500, but everything after that, so in the second sample, only the first 588 things are 1s. Everything after that is 0. In the next one, only the first 563 things are 1s. Everything after that is 0, ... So we want to make sure we just use this mask to mask our data. So we do dot shape. One thing, just to keep in mind, print our output dot shape. So the output is right here, right? The original output of this convolution, which produced this thing. Look at the output dot shape and look at our mask dot shape. We're missing a couple dimensions here, right? We need to unsqueeze to broadcast over our channel dimension and over the sequence dimension, or sorry, the mel bins dimension, right? Our feature dimension. So we'll do a quick dot unsqueeze. So let's do mask is equal to mask dot unsqueeze 1 dot unsqueeze 1, and we have those dimensions lined up, so we can print the output, and then we're going to do output is output dot output times that mask, and then print the output. And all we've done is in the original output, we had our data like this, right? This is our original data, but notice that in our second sample, we computed stuff in this masked area, right? This stuff is not valid because this used to be mask tokens at the beginning, right? The padding tokens at the beginning. So we need to go ahead and mask this area out because all of this used to be pad in the original audio before we applied it. And so that goes ahead and just multiplies those by 0 because they're invalid. And so that is essentially a mask convolution. We have a convolution, we apply it, we look for the areas that are valid in the output and zero out the invalid areas. Okay, so now let's go ahead and write the mask convolution that just does everything we just talked about. So class masked conv2d nn.conv2d. So this is just going to be a wrapper on the existing convolution. I'm just going to go ahead and just copy some of this stuff so I don't have to write it all out. These are the standard inputs to the convolution, and we're going to be initializing our class by inheriting our existing convolution, right? So we have all the standard methods of the existing convolution. So now that we have that, we're going to do def forward self x and sequence length, right? We need the sequence lengths for this input, and then we're going to output the valid sequence lengths that come out of it. We're going to have batch size by channels, by height, by width, x.shape, standard form for a convolution. And then we'll have our output sequence length is going to be equal to self.compute out sequence length. Nice. So let's go ahead and write that method. So this method is just the formula we had from before. So I can just, paste that in here. So we're going to have def compute out seqlen self sequence length, and return that. This is the formula we wrote earlier. The only difference is we're accessing self.padding, self.kernel size, self.stride. So what are the stride, padding, and kernel size for this specific convolution? And also, we really only care about the horizontal direction, right? What was the padding in the horizontal direction, the kernel size in the horizontal direction, the stride in the horizontal direction, because the padding was added horizontally, right? So we're just accessing because everything's a tuple, right? Like we had the convolution up here, we had the kernel size in the horizontal and the vertical direction, the stride in the horizontal vertical direction, padding, horizontal vertical direction. So we're just setting it up that way and just getting our final outputs for the horizontal direction specifically. So that's what that gives us. Now that we have all that, just rewriting the stuff from earlier, we can then go ahead and do conv out is going to be equal to super dot forward x. So this is just going to use the original forward method of our original convolution on this data. So that sets that up, and we're kind of good to go there. And all we need to do is mask out the invalid portions of the input, right? The pad portions of the input. So let's just create a mask. If we do mask is equal to torch.zeros, let's create a 0 tensor that's in the shape of the batch size by the output sequence length dot max. So whatever the longest sequence length is, which will just be the output of this convolution, but that's fine. Whatever the longest sequence length is, we want to go ahead and create a tensor of that shape, and we're initializing it as zeros. And now what we're going to do is loop through every sample and just set the valid parts of every single batch to 1, right? So let's go ahead and do that. Of course, if we create a tensor, we want to make sure it's on the correct device. So there we go. And we're going to do for I length in enumerate output sequence length mask for that specific sample up to that length only. It's going to be set to 1. So we now have a tensor of zeros and ones that looks exactly like the mask we had created up here. Exactly this mask up here, where we have ones for valid outputs and zeros for invalid outputs. Well, that's what I did, right? I just created a 0 tensor and set everything to 1 where they are valid. Nice. It's being stuck again. Sorry about that. All right, so now that we have all of that, we created our mask. We can now multiply our output. So our mask, just like before, mask is going to be equal to mask.unsqueeze1.unsqueeze1. Just add those dimensions in. And we'll do conv out is equal to conv out times mask. Go ahead and just mask out those invalid portions, set them back to 0, and we'll return conv out and the output sequence lens. Oh, there should be 1 right there. Perfect. So that now that we have that, we're going to go ahead and write our convolution feature extractor, which is a stack of 2 convolutions. And all I want to do is copy the NVIDIA implementation. So I actually have seen a couple of different implementations of what this feature extractor should look like. So I'm just going to use the NVIDIA one for our test case here. It's fine. So we're going to do class convolution feature extractor and module, and it's going to be a stack of essentially 2 convolutions with bash norms in between, and we're going to be using a hard tanh as our activation function because that's what they found to work best. So we're going to be doing our setup as super convolution feature extractor self dot init, and we'll have self dot oh, my bad, we missed the definite. Oh, self, and we'll have in channels is 1, out channels is 32. That's just the default from, again, the NVIDIA implementation. So that's what we're using. Okay, now that we have that, we'll have self.conv1 is going to be that masked conv2d that we wrote earlier with in channels to out channels. We're going to use a kernel size of 11 in the vertical direction and 41 in the horizontal direction. So you can imagine as a pretty large receptive field in the horizontal direction, and we're doing some downsampling of our vertical direction. So we have 80 mels right now, and it'll downsample to like some number of mel bins after we have this. So that's our kernel size. And we're going to be using a stride of 2 and 2, and we're going to be using a padding of 5 and 20. After we do that, we will have a self dot batch norm 1 is nn dot batch norm 2d out channels, right? Just like that. So let's give this a try. We still have to do one more, but we'll do that in a bit. We'll write a def forward self x and sequence lens, and we'll have a x sequence lens. So this will be the output sequence lens of the first convolution, but that's fine. It's going to be equal to self.conv1x sequence lens, right? Just like we wrote earlier. Print x.shape, print sequence lens, and let's also print x.shape before we do anything, and print sequence lens. There we go. And so we can pass into, let's create a convolution feature extractor. And we can create a pass into here our batch, our input values from before, and our batch sequence lens. And we get something like this. So this was the original data that we were working with. And we can see that after we do a convolution, after we did this convolution, we have the same number of batch, of course. We went from 1 channel to 32 channels, so 1 to 32, but our 80 mel bins are now downsampled to 40 mel bins. So good to see. And we can see our 1276 was downsampled to 638. So we've downsampled both in this direction and we've essentially downsampled the number of bins and our number of time steps. But of course, the bins are fine. We can change that however we want because there's no padding there. But in this 638 time steps here, only some of these were actually valid, right? And some were invalid. And our masked conv2d already handled that for us by masking out all the invalid stuff. So if we print out actually x, you'll see we'll have a bunch of zeros, right? So these stuff were invalid. So that's why they are zeroed out by that mask ahead of time. So we are good to go. We can see our final output. So our updated sequence lengths are this. So we have 638. only the first 589 is valid, only the first 564 is valid, only the first 558 is valid, only the first 501 is valid. So when you do convolutions again, there's pad, right? So everything from 589 to 638 is padded to 0 because we masked it out. So only the valid portions should again occur, right? Be computed on, and everything else should be masked out. Once again, just repeating it exactly how we did it, just on the output of the first convolution. So let's go ahead and apply that in. So first, x is going to be equal to self.batchNorm1 x, and then they found that the hard tanh activation function seemed to work best, so we're going to just do that, functional.hard tanh x, and that's our first set. After that, we're just going to repeat this all again, self.con, but now it's going to be con2, batchNorm2, and they use a smaller receptive field of 21. They use a stride of 1 here, and they use a padding of 10. And actually, one detail that I missed is they also don't include any bias on these convolutions. So we're going to see bias to false on both of these. So there's no bias terms. That's fine. It doesn't affect the shape of the data we're working on. And then that means we're going to repeat all of this stuff once again. But this is going to be batchNorm2, conv2, and we print our final x.shape. And we'll keep the original x.shape. Looks like we have a bug because we have out channels, right, going into here. So let's update that. We can see we are now down to 20 mel bins. So we started with 80 mel bins. We went down to 20 mel bins, but we have 32 channels now. So that's one change. And we went from 1276 time steps down to 638 time steps. So we've downsampled in the temporal dimension as well, where all the invalid parts have already been zeroed out ahead of time. And so now is the final part. We need to set this up for the RNN. And recurrent neural networks typically work in the dimension of batch size by sequence length by embedding DIM. What I have is batch by channels by height by width. But I know this 638 is my temporal dimension. So let's go ahead and just do a quick transpose here, right? Let's move things around. X is equal to x dot per mu. I want batch size by my sequence dimension, which is 0, 1, 2, 3, so 3. And then we'll leave the other ones alone, so 1, 2. So we have batch size by sequence length. And what we have is 32 channels, and each channel is a 20 features, right? Some compressed representation. So why not just flatten it? Dot flatten 2. So this is our final output. We have 5 samples, 638 time steps, and each time step has 640 features, right? So that's our embedding DIM essentially, or the number of features at every time step. And it's 640 because we took the 32 and the 20 and flattened them. And so what I can store here is self.output feature is going to be feature dim is going to be equal to 20. I already saw that. The MelSpectrogram went from 80 to 20. And then my final self.conOutput features is going to be self.output feature dim times self.out channels. So that's just telling me that's essentially, this is the 640 that we have here. I'm just hard coding it just to keep it simple. Of course, if I change any of these numbers, none of this is valid anymore, right? I have to recompute it specifically for my thing. But that sets us up, and we can finally return x and these sequence lengths. And these sequence lengths, again, tell me which ones are valid and which ones are invalid, because the RNN is going to care about that in the future. So we have no attribute out channels. This should be not self, just, there you go, out channels. And we are good to go. So this is our, we can just comment this out. We don't need this anymore. That's our convolution feature extractor on our spectrograms. Now that we have that, we need to do our RNN layer. Now to do the RNN, we need to quickly review packed padding. If you've never seen this before, it's pretty straightforward. So what we're going to do is our conv is the, let's just copy what we had from earlier. I should have pasted it down here. So this is what we had just done earlier, right? We have our convolution output and the output sequence length. So we have conv out. These are my outputs. You can see stuff, this is the final output. It's been transposed and moved around, so you can't see those 0 paddings anymore. But if we look at the shape real quick, that's our final shape, right? 5 by 638. It looks like I have a print here. Let's get rid of you. So that's my final output, and this is what I'm going to be passing to my recurrent neural network. a batch size of 5 by 638 time steps, and each time step is represented by an embedding dim of 640. Typical sequence problem. The thing is that which one of these 640s is valid and which ones are not valid? Well, that's determined by the output sequence lengths, right? These are the valid tokens. For the first sample, only the first 537 is valid. For the next sample, only the first 588 is valid. Then 563 is valid, ... So these are my valid and invalid tokens. So now that we have all of that, we can do packed con out. It's going to equal to, and let's just verify here, 510. Okay, yeah, we are good. So our packed conv out is going to be equal to nn.utils.rnn.pack padded sequence. So it's a built-in method. And what we're going to do is provide it the conv out. So these are my outputs. I'm going to provide it my output sequence length. So output sequence length. And of course, batch first is true because I just prefer that. And if we print out our packed conv out, you're going to see something interesting. You're going to see first our data that's essentially just been all concatenated together, right? So it's just one big sequence. And it says that for these time steps here, all 5 samples are valid. Like all 5 samples are valid. But after that, it becomes too long. So let's kind of look at it from this picture here. For the first part, like everything up to this time step for all the samples are totally valid. So all 5 samples are valid. But after that, this one's kind of run out. So in the next one, only up to here, all 4 samples are valid. But after that, this is invalid. So up to here, only these 3 samples are valid. But after that, only these 2 samples are valid. And then of course, in the last one, everything is valid. And so that's the key idea, right? This is why we sorted it from greatest to least, because we can then use the packed method, which essentially does this. We have 5s for all of this here. We then have only after this time step, only the first 4 are valid. And then after that time step, after this time step, only the first 3 are valid. At that time step, only the first 2 are valid. And after that, only the first one is valid. So it tells us which indexes are valid at the different samples. And so that's the main idea. That's how the packed sequencing works. And RNN accepts this by default. And this, remember, it removes all of those extra pad tokens. We no longer have those padding related, so the RNN doesn't need to waste time processing pad tokens that have no information. So this is a key step of training recurrent neural networks. We're doing class RNNLayer, nn.module, def init, self, our input size, which we know is 640, but that's fine. And then the hidden size, let's just pick 512 because that's what the NVIDIA implementation used, I believe. Super RNNLayer self.init. And let's just store self.hidden size is the hidden size. Self.input size is the input size. And then we have self.rnn is equal to nn. We're going to use an LSTM here just to match it, but you could try GRU or anything else. Input size is the input size. The hidden size is the hidden size. We have batch first is true because that's how we set the data up. And we'll be using a bidirectional model, right? We'll be using bidirectional because in this case, when we train our neural network, we're passing the entire input in at once. So future steps can look in the past steps, but early steps can look into the future steps. So bidirectionality is totally valid in this case. This would not allow us to make DeepSpeech2, or at least this implementation of DeepSpeech2, a streaming model where it's like transcribing as you're going. For that, if you want to make a streaming model, you can only look to the past to predict, right? Because there is no future, because data is coming in as you're saying it. But for now, this should be totally fine. So we have our LSTM, and then we'll have a self.layer norm is what they use. So nn.layer norm, and it's going to be 2 times hidden size. Why is it 2 times hidden size? Because if we do a bidirectional, whatever hidden size you pick, you're going to have the hidden size going in one direction and then the hidden size going in the reverse direction. And then PyTorch will just concatenate them together for you. So you can go ahead and take a look at, for example, LSTM, Torch. If we look at the Torch implementation of the LSTM, just to have some clarity, we can see that the output is going to be if D, so D is 2 if bidirectional is true, otherwise 1. And where was it? Yeah, the output will be D times, oh wait, actually that's not helpful. We want to look at, here we go. The final output will be D times H out if you have, D set to 2, if it's bidirectional. Otherwise it's 1. So we'll have 2 times the set H out that we set. So that's fine. If you're a little bit confused about LSTMs or don't know about them, I have an entire video talking about the different ways you can use LSTMs. So I will also link that above, and you can look, and also link it below, so you can take a look at that if you have any questions about how the LSTM works. So now that we have the layer norm here, we're going to do def forward self x sequence lens, right? And first we're going to do batch sequence len embed dim is x.shape. And then we're going to do a packed x is going to be nn. So this is us doing the packing. nn.utils.rnn.pack padded sequence x sequence lens. And then again, batch first is true. And then what we're going to do is take this packed data and pass it to our LSTM. So we're going to get our output. We'll also get the hidden and cell state, but we don't really care about that. So we're going to ignore that. And then self.rnn packed x. Right? Go ahead and pass the packed data in. Now what we're going to do is unpack the data so we can do the layer normalization on it. So we're going to do x, and we don't really care about all the other stuff the unpacking releases. So it's going to be equal to nn.utils.rnn.pad packed sequence. So notice here, we're packing a padded sequence. In this case, we're padding a packed sequence. So it's exactly backwards. So it's just undoing that process. We're just going to go ahead and repad the data and essentially unpack the data. That's the main idea. So it's going to be based on the output. Our total length is equal to the sequence length, right? So that's the final output. And then batch first equals true. And that's our unpacking. So basically the main idea is we're packing it here just so this RNN isn't wasting time processing a bunch of pad tokens. But now that it's done, we can go ahead and unpad it and apply our layer normalization, self.layer norm x, and we return x, just like that. And that's essentially our entire setup, right? That is our RNN layer, a single RNN layer that does all of this. So let's just go ahead and define our DeepSpeech2 model. So class DeepSpeech2, or at least a good, something pretty close to it. It may not be exactly DeepSpeech2. Again, I've seen so many variants of it. I'm not exactly sure what the specific ones are, but that's fine. This should be close enough. Conv in channels, we're going to have a one input channel, conv out channels. We set it to 32. We had a RNN hidden size was 512, and then the RNN depth is, in this case, 5. And the RNN depth is essentially this. In this picture, we don't have just, where'd the picture go? Here we go. In the RNN, we don't have just one recurrent neural network. We have a bunch of them stacked on top of each other, right? So this is the depth of the RNN. And so this is me just doing exactly that, grabbing, defining that I want 5 of them in this case. But you could try more, it just takes longer to train. So first, super DeepSpeech2 self.init. And we're going to have self.feature extractor is self.feature, or sorry, this is going to be convolution feature extractor. And we're going to pass in conv in channels and conv out channels, just as we defined earlier. And then we'll have self.output hidden features. It's going to be self.feature extractor dot conv output feature. So this is that 640 that we had. We have a final 640 feature output in our convolution extractor. So now that we have all of that, let's go ahead and define our RNNs, self.RNNs, right? RNNs is going to be nn.module list. It's going to be just a bunch of RNNs. It'll be the RNN layer, which is already doing the padding and packing and all of that fun stuff for us. Input size is going to be self.output hidden features. And this will only be true if I is 0, right? So in the very first RNN, it's going to be 640 input features, but then we know that the output of this, is going to output 2 times the hidden size, right? 2 times the hidden size, which means all the future layers need to accept 2 times hidden size. So we're doing 640 if I is 0, right, for the first one, else 2 times our RNN hidden size, and then hidden size, all right, let's just go to the next line. Hidden size equals RNN hidden size for I in range RNN depth, right? So all we've done is create a bunch of RNN layers. It's just the first RNN layer will have 640 input, and in this case, 1024 output, 2 times 512 because it's bidirectional. But all the other ones, if the first one outputs 1024, then the next one inputs 1024. So after that, the input will just be 1024, and then it'll again output 1024. Then it'll input 1024, and then output 1024 over and over again. So we're just dealing with 1024 dim vectors. And now that we have that, finally, we need our classification head. Self.head is going to be equal to nn.sequential. Just a bunch of layers. It's going to be nn.linear. The input is going to be, again, 2 times RNN hidden size, right? The 1024 vectors. And we're going to go to RNN hidden size. We'll throw in a nn.hard10h just to make it the same. And then again, nn.linear. And it's going to go from RNN hidden size to our vocab, right? So for every time step, we want to predict what is the letter at this time step. What's the letter? What's the sound? Which letter is said at this time step? What's the letter said at this time step? What's the letter said at this time step? And so this will be our tokenizer.vocab size. In this case, it was just 32. And so we have def forward, self, x, sequence length, right? And all we're going to pass in is x final sequence length is going to be equal to self dot feature extractor x sequence length, and that essentially does the convolution. We'll get our batch by number of time steps by 640, essentially, right? 640 dimension vectors. And now we're going to loop through each of the RNNs, passing our data through. So for RNN and self.RNNs, we will just do x is equal to RNN x, and we're going to pass in our final sequence length. Because once we are done with the convolution, the RNN never changes the length of our sequences, right? Nothing like that happens. So it'll just stay this final sequence length over and over again for each one of them. And it'll do the padding and the packing, and then it'll unpack it and pad it again, all in that RNN layer that we wrote. And lastly, we'll have x is equal to self dot head x, and we return x and our final sequence length. We're going to need that for the loss function in a bit. And this is our final model. So model is RNN, or actually it's DeepSpeech2. Looks like around the comprehension target, it's going to be RNNLayer. Maybe I just typed it wrong. Let me just put this here. There you go. Yeah, I was just missing a comma or something. Okay, so we're good. So we have our model, and our model looks like this. We have a convolution feature extractor, which has a masked convolution, a batch norm, another masked convolution, another batch norm. And then we have a bunch of RNNs, where the first RNN is going to output 640 or input 640 things and output 512, but it'll be actually 512 times 2 because it's bidirectional. And so every model after that is going to input 1024 and then output 512 times 2, 1024 over and over again with a bunch of layer norms in between them. And we have our final output head, which is going to output to 32 possible things that it could be. And this is exactly what our setup is for training. So now to train, pretty simple. I'm going to go ahead and just copy a bunch of stuff that I don't, it's pretty boilerplate. So we have our batch size, how many iterations we want to train for, how often do we want to evaluate, a learning rate, how many workers we want to use, and a device we want to train on. Here's the path to my data, and here's my data set for training. So I'm training on all 960 hours here. And I'm going to validate on my 2 test splits, right? Test clean and dev clean. So that's what I'm testing on. I wrap them in the data loaders that we have here with the collate function that we defined earlier. I have my deep speech model here. I get my number of parameters, how many parameters am I training this model, and I just, throw in I'm using the Atom Optimizer, which is fine, and I just throw in a scheduler because why not? So we are, and we'll have also the num training steps is going to be equal to the training iterations. There we go, missed that. So the standard, setup for most neural network stuff. So let's go ahead and write a training script. Training script's going to look just like basically every other training script we've ever done. So we're going to do best val loss is going to be np.infinity, right? So let's go ahead and initialize it like that. Train is true. Completed steps is 0 because we haven't trained anything yet. Train loss validation loss is 2 empty lists, just like that. And then we will do a progress bar, p bar, is going to be equal to tqdm. It'll be range training iterations, just like that. Nice. So now that we have that while train, right? So while train is true, we're just going to go ahead and do our training losses, validation losses. Just go ahead and create a list so we can store as we're going. And we're going to do for batch in train loader. Just throw a break in there. So again, if we remind ourselves, print our batch out. This takes just a second, but we get all this information, right? We have our input values, which is the MelSpectrograms. We have our sequence lengths for all of the different samples. We have our labels, which are already concatenated together, and we get how many, basically the first 246 things in this label, sequence of all the labels concatenated, is the first sample, and then 193 is the second sample, 194, the next 194 things is the third sample, dot, dot, dot. So that's everything. So we can then go ahead. Oh, it's been training. Let's just set this to train equals false at the end, just so it doesn't keep going and breaks the loop. All right, so first thing, logits input lengths is equal to len g lengths is going to be equal to model, and into it we're going to pass in the batch input values dot to device, right? So pass in the data, and also pass in our batch sequence lengths, which we only really use for indexing, so we don't really care about which device it's on. So there we go. Looks like I didn't define a device. Oh, I guess use uppercase device. So let's do that. To device. All right. Good. So now we have our print logits.shape and print input lengths. So we have data in this shape, 32, batch size 32, sequence length of 644, and we have 32 possible outputs for each thing because our tokenizer had 32 possible tokens. And here are the sequence lengths of each of those samples, right? Valid sequence lengths for each of those samples. And we're going to be needing this for the CTC loss. So what we're going to do is our log probs is going to be equal to nn.functional.log softmax. So we're going to have to take a softmax. We did to convert logits to probabilities, but then we're going to take the log of it to make it a log softmax. And this is stable softmax, so I'm sure they're already handling like some of the annoyances with log in here already. And dim equals -1 along the last dimension. So if you print log probs, we'll now get probabilities along the, or log probabilities along the last dimension. So we are now good to go. Those are our log probabilities. And again, if we print out log probs.shape, you'll see that we have batch size by sequence length by number of possibilities that we can have, but CTC expects it, if we go back to the CTC loss, CTC expects it in time by batch by number of classes, right? So time batch number of classes, but we have batch time number of classes. So we just need to move things around a little bit. So log probs is equal to log probs dot transpose 0, 1. So now we have the shape of time by number of classes, or time by batch by number of classes. So we go time by batch by number of classes. Let me make the batch size a little bit different. Let's do a batch size of 8 just so our numbers are different. So it's clear. So we have time by batch by num class. This is just how PyTorch expects the CTC loss. And so our final loss is going to be nn.functional.ctc loss, and we'll be doing it on the log probs equals log probs. So there we go. We're then going to have our targets is going to be equal to batch labels. Oh, it should be lowercase labels. And again, this is our option, right? Our targets could either have been basically a batch by sequence length thing, where we have essentially zeros or essentially pad tokens or something like that, indicating our things. But we ended up concatenating everything together. Our targets, if we remember, let's look at it right here. So our labels look like this. It was just one big sequence. If we look at the len of this, we have 1649 things here. And if we print batch target lens, or what did we call it? Let's double check. We called it target lengths. Okay. So if we look at our batch target lens and do the sum of that, we'll get the same number, right? So it's the same number. So it's up to us. We're deciding to do it this way. Basically, we'll give one long tensor with all of the targets, and the target length will provide like which parts of that target go with the first sample, second sample, third sample. We could have also done it this way. Both ways are totally valid, but this way is just easier because it's all one thing and we don't have to deal with padding of our targets or anything like that. So it just makes our life a little bit simpler. So we will now have our targets is batch labels. Of course, this needs to be on the device, otherwise it won't work. Our input lengths is going to be equal to the input lengths. Our, oh, missed a comma there. Our target lengths is going to be equal to batch target lengths dot to device. And then we have our blank token, right? What are we using our blank token? We're using the tokenizer dot pad token ID. We're just going to be using the pad token as our blank token. You could also just like actually have a specific token for blank, but that's fine. We're just going to use the pad token as it for now because we're not using it for anything else. And we're going to do reduction equals mean, right? So we want the average loss at the end. See if that works. So that should give us our loss. So that's our loss value right there. And then training is identical to everything else. So now it should be pretty easy. So loss.backward. Optimizer.step, optimizer.zeroGrad, set to none equals true, and scheduler.step, right? Go ahead and step that as well. And there we go. That is our setup for updating the model. We can then go ahead and just do the rest of our stuff. Training, losses, and we're going to do .append. We're going to store in our here loss.item, and then completed steps plus equals 1, and then pbar.update 1, because we've completed a step. And now to evaluate the model, it'll be identical, so I can just go ahead and copy the rest of the stuff in, because there's nothing new anymore. So to evaluate, very simple. Once we've reached an eval iterations, go ahead and evaluate, set the model into evaluation mode, loop through our test loader, with no grad, get the same things, compute the log softmax, compute the loss, store the validation loss, average it all up. If our valid loss is less than the best val loss so far, go ahead and save it, and then just print it out, reset it, and set the model back to training mode. And once you've hit number of training iterations, go ahead and exit, right? Say train is false, and complete training. And that's it, right? So identical to what we had earlier, just for the validation. So we could verify this works. There we go. So this will work just fine, but of course, no one wants to watch a training loop for 2.5 hours. And this isn't even the best training run. You have to train for a little bit longer to get better results. So let's just quickly look at the loss curves real quick. You'll get something that looks kind of like this. You can see they both decrease. You'll start to get a little bit of overfitting happening, but there's other methods that help with this stuff. Notice that we never did any kind of augmentation. Like in image training, we typically have like random flipping and we have color jittering and that sort of stuff. So there's all sorts of spec augments that we can also apply to this model, but I left that out just for simplicity. But that's essentially doing speech-related or audio-related, audio-specific augmentations on those spectrograms. But for now, that's fine. We're not going to bury ourselves in too many details. Oh, let me open that back up again. So yeah, so that's what our training loop will look like. I've already trained it, so we can go ahead and let's just test it out. We're going to do model is equal to DeepSpeech2, and we'll do model.load state dictionary, torch.load, and we'll do the best weights.pt, I think is what I called it, and weights only equals true. So that's fine. Go ahead and just loaded my weights. And let's just write a quick inference script, right? So inference script should be pretty easy. We can honestly copy this because we've written all this code for everything we've done, except for one line, which we'll look at. So we have our inference script. Go ahead and take an audio file. We have our transforms here, same as before in our data loader. We go ahead and load our audio, update the sampling rate or resample to the sampling rate we want, go ahead and convert to the MelSpectrogram, normalize it, add in a batch dimension, get that source length, right? Basically what it is, set the model device to GPU, that's fine. Go ahead and inference it, go ahead and do, and this is where it gets a little bit more interesting. Let's comment U2 out and let's just do a quick example. So we're going to do the right here. Copy U2 in as well, comment U out. So we can do our print. Let's do it up here. Print pred logits.shape. Right, so this is our final output for this one sample. We have 418 samples, right, or time steps, and each time step has 32 possible predictions. So let's go ahead and see what that looks like. We can do dot, first of all, we can do dot squeeze to get rid of that extra dimension, and then dot argmax axis equals -1. So this is known as greedy decoding, because what I'm doing is grabbing the most likely character at every time step. Greedy decoding is totally fine, but again, in a lot of these applications, there's better methods like beam searching and stuff like that, which we'll explore in a future video. For now, this is just fine. So in greedy decoding, we're just going to grab the most likely prediction at every time step, and that will give us this. So this will be the pred tokens, looks like that, dot to list print pred tokens. And we can see these are predictions. We have a bunch of zeros. We have some, these two 11s will collapse into something. We have a 5, a 0. So we have some pad tokens. These 4s will collapse. So we have some 11s, which will collapse. We have an 8. We have some more zeros, 23, dot, dot, dot. So this is all our stuff. And essentially, we need to collapse all the repeating stuff together and then get rid of all the zeros in between them, right? So we could easily write a method that does that, or we can just use the wave2vec tokenizer, right? So the tokenizer decode method from wave2vec already does that for you. So we'll go ahead and just take advantage of methods that exist already, and we can go ahead and print it out. And you'll see we get something pretty close. He hoped there would be stew, so it looks like in the true transcript is stew, but our model predicts stow. For dinner, turnips, the true transcript was and, but we predicted ond. The true transcript was carrots. We got carrots, but we misspelled it. And bruised potatoes and fat mutton. We did mutton, right? So close, but not exact. To be ladled, so that's kind of that's all correct. And the thick peppered flour and flour. That's a tough one, right? Because these are synonyms, flour and flour. But it's cool. And then we have fattened. We have fattened sauce. So this leads to a word error rate of 21%, which is actually not too bad. It's definitely usable, but state-of-the-art models are getting like 7 or 8 or like 4% word error rate on these data sets. But this is a pretty early on model. It's not really comparable to some of the bigger models like Whisper and wave2vec and stuff like that today, but it's fine. It's just to give an idea. So you can see we're getting something pretty close, right? We are transcribing relatively well. This isn't too bad. Of course, it'd be most interesting to see how our model's doing overall. So we can just like loop through all of the data, all of the testing data, inference and just grab all of the word error rates. This takes a few minutes, which is fine. In the end, we'll get an overall word error rate of about 18%. And you can see it's not like it's getting the words wrong, it's just misspelling them a little bit. This is why adding LLMs to speech models have become so popular today, because LLMs are great at spelling, because that's what they do, they write. So kind of going from speech to just writing stuff out is great. Another way to improve this is instead of training on a character, because it's essentially a character level model, each token in our data is a single letter, A, B, C, whatever it may be. If we train on n-grams, like something like a BPE tokenizer or something like that, you can expect to again get a slight improvement over this, because instead of spelling it out one letter at a time, you'll be spelling it out a couple letters at a time, which could be better. Either way, I'm going to call it here. This is essentially again, re-implementation of deep speech. The main things that I wanted to make sure you took away from this is that to train a model on speech, there's essentially two things that always show up. The first thing is when we do our convolutions on our audio, we always mask out the invalid portions, the padded portions of the convolution. That's important. And then the second part is whenever we're training the RNN in this case, we have to do this packed padding stuff just for efficiency's sake, because there's no point of iterating through pad tokens, right, or padding areas of our audio. In the transformer, when we do this in the future, we'll be doing attention masking, right, because that's how the transformer deals with pad tokens. A little bit different, but same principle. But yeah, this is a very early example, or a good example, of a solid speech recognizer. In one of our future videos, we'll be doing a full reimplementation of the wave-to-vec architecture, which is significantly more complex than this. So I will see y'all in the next one.